So, Paul, in this series of lectures, we're going to be talking about the part of the universe that I really like, the deep, dirty, secret underworld of black holes, neutron stars, supernovae, the violent universe. This is really what I love about astronomy and cosmology.
Yeah, and to my mind, this whole story really starts in the early 19th century with the discovery of something very strange and very massive orbiting the star Sirius B. So we're going to start off with that story now. The story starts actually hundreds of thousands of years before. People were trying for a very long time to measure the parallax of stars. The idea is as the Earth goes around the Sun, as Copernicus told us it is, our point of view varies, and so the stars should appear to wobble backwards and forwards.
This is the old thing where I always go like this with my thumb, and I blink eyes, and my thumb moves relative to the background.
Yep, and no one had ever discovered this. The stars just did not appear to move. As the Earth went around the Sun, the stars did not seem to move to extreme precision with regard to each other. Right. And in fact, the Inquisition used that as an argument against Galileo. They said, look, if the Earth really is going around the Sun, the stars should appear to move, and they don't.
Right, and even the Greeks used this to try to figure out how far away things were, and
it's been used successfully to work out how far away the Moon was and the Sun and things like that. But for stars, we couldn't measure it. And people have been trying for a very long time. There have been lots of false claims of discovery, but the telescopes at the time just weren't good enough. And that's where a German by the name of Utzschneider comes in. He, back then in the early 19th century, the British had a monopoly on high quality optics. All the best telescopes and surveying instruments came out of the workshops mostly in London. And the Germans weren't very happy with this. There was huge demand across Europe, mainly for military surveying purposes, for precision optics. And so it turned out that Utzschneider had been called to a collapse of a house, and this guy had been rescued from the ruins after several days. You see nowadays there are earthquakes and they find someone drawn and there's huge media coverage. He was the equivalent of that when this house collapsed. And Schneider and the Prince of Bavaria decided to sponsor his education. Okay. And he, this guy is Fraunhofer, a very famous optical engineer and astronomer. We'll hear lots about him as time goes on. And he was given the job of setting up a company to rival the British and develop superb optical instruments. And he set about using a different approach. Previously, it had been very much trial and error. Let's take the sort of glass. Oh, maybe this one fits. Just trying lots of things. He decided, yeah, that's good, but we need to combine it with some actual real understanding of the physics of light.
Right. So Fraunhofer was the first person to really go through and be a serious optician. And that sort of caused a revolution in our ability to do astronomy.
Yes, and he built brilliant telescopes. We haven't got one of his telescopes here at ANU, but we have got a very similar one. So let's go and have a look at that and talk about some of the innovations that he came up with. A common mistake people make when buying telescopes is they get a really powerful telescope but put it on a really flimsy mount. Fraunhofer wasn't going to make an elementary mistake like that, though many of the earlier telescopes did. For example, the Great Melbourne Telescope, the biggest in Australia for many years, was a very powerful telescope on a really shaky mount, so they never get good data. This is the sort of mount Bessell invented, what's called a German mount. It's very sturdy, there's concrete, there's thick bits of metal and bars, counterweights, everything is counterweighted so you can push a telescope around with only a very small amount of force. There's this axis here, which points at the celestial pole, in this case the south celestial pole, because we're in the southern hemisphere. And so as the telescope rotates around this axis, it can track anything across the sky with just a single rotation. And there's the declination axis, this one here, which comes through there, which allows you to point north or south in the sky. And everything is counterweighted. You see the counterweight over there, so it's easy to move. In fact, there's an even better trick. The telescopes were designed to be able to automatically follow things as they move across the sky. Actually, of course, they're not moving. What's happening is that the Earth is rotating. Here it's powered by clockwork. We wind up a weight here, we wind up a weight which is in the middle here. And as the weight falls, it drives a set of gears controlled by the spinning regulator, which will automatically rotate the telescope to cancel out the movement of the Earth and keep you lined up on target. One innovation in Bessell's telescope was that the main lens was actually cut in half. And the two halves are put on sliders, which could move up or down with respect to each other, and you could measure off little screws precisely how much you moved them. This meant you got two images of whatever part of the sky you're looking at rather than just one. Why would you possibly want to do this? Well, the idea was they were trying to look for parallax, a very slight wobble of stars, and the way they measure it is by reference to other stars in the field. And what you do is you take the star you're interested in and line it up with the second image of another star in the field. And then over the year you could see by how much you need to tweak the adjustment to keep it lined up, and those tiny tweaks would tell you the amount of parallax.